All right, in this lesson, we're going to kind of begin our lesson on electrical, and we're going to look specifically at Ohm's law and the power law. So those are our two things we're going to look at. We're going to start with a few terms, and by the end of this lesson, you should be able to calculate with current, voltage, and resistance, as well as power in watts. So we're going to cover some of those basic pieces. You've likely done this with Jeff already at this point. If you haven't, you will be doing it shortly in your electrical unit with him. So it's really good to supplement what he teaches and reinforce the concepts. So first of all, we have some main terms that we need to look at. We have voltage, current, resistance, and power. Now, voltage comes from a battery source. That's usually fairly easy to remember. We're used to picking up batteries that have voltages marked on them. Another word we see sometimes for voltage is electromotive force, also called EMF. Now you may see that, I'll make that note here, you may see EMF come up in a quiz. If you see EMF in a quiz, it's electromotive force, and all I'm telling you is this is the voltage that you're going to have. And typically you'll have volts associated with it, but if it asks you for what is the EMF, you are looking for voltage. That's electromotive force. And that's a term that's used more specifically in the trades than it tends to be used in general high school classes or other places you might have been introduced to some of these electrical terms. Now, current, we're fairly familiar with. When you're thinking current, electrical current, you can think of it like water. So it's a flow. Instead of the flow of water, it's the flow of electrical charge. So voltage is the result of charges being separated. Attraction causes those charges to move through a circuit back to the other side. So charge moves from negative around to positive. All right, so that's the definition of current, although you will find there's a couple ways that current is stated, and conventional current actually is stated from positive to negative, which is actually incorrect, but it's something that's kind of stuck historically. But the flow of current is typically from negative to positive. There's the extra negative charges. They're the electrons that travel around. You're not going to have to worry too much about current flow for me, but it may be something that you will discuss further with Jeff in his class. One important thing about current is current requires a closed path to flow. If you do not have a closed path, current will not flow. So that's essential. You have to have the wires connected. Switch has to be closed. If a closed switch means the wires are connected, open switch will mean the wires are open. If you have an open switch, current will not flow. The unit for current is always going to be in amperes, or we often say amps. Resistance is another key term, and this is a picture of some just basic resistors. Resistors slow the flow of electricity. So you can think of, say, a pile of rocks in a little if you're at the beach building channels, you fill it up with water and you watch the water go down. And if you put a little bar of sand or a little pile of rocks somewhere in those channels you've made, it'll slow the flow. That's a resistor. So you think of a resistor being that way. Resistance can be caused by multiple things. You can have resistance due to a resistor. You can have resistance caused by the load on a motor. It could be caused by a light. Light bulbs are a form of resistor. So there's multiple different things that can cause resistance. So resistance is anything that's going to decrease current in a circuit, okay, or at least decrease current in a particular section of a circuit. And then power is just the rate at which electrical energy is converted into work. Okay, so we'll look at watts for being our power. Watts are really joules per second, so it's the amount of energy per unit time that is used. So you'll see a couple questions with power. Light bulbs, they're rated by wattages. So the more watts, the more power it consumes, the brighter the bulb. All right. Now there are some common symbols that you should have a look at. Symbols that we will see, sometimes we'll see a switch. A symbol similar to this is quite commonly used for a battery. Lamps, this is a common symbol used for a lamp. Sometimes we'll also see a lamp as a circle with kind of like a little loop in the middle, and that can also be a lamp. A voltmeter is just a device to measure voltage. Ammeter measures current. Resistors, there's two different ways to see them. I typically I will use the zigzaggy line. Sometimes you'll see resistor written as a box. A variable resistor, you could have the same thing. You could have the zigzaggy line with an arrow through it, or it could just be a box. What a variable resistor is it's a resistor that you can control. So something like a switch that you can control would be a variable resistor. And then motors are often just a circle with an M. Typically, we'll just use a resistor rather than being specific as to what kind of particular device it happens to be. We use resistance kind of into the general term. All right, so now let's get into Ohm's law. So Ohm's law states that voltage is related to current and resistance. So we see this formula, E equals IR. Now you may have seen this with Jeff as V equals IR. It's exactly the same formula. A lot of books will use E for, do you remember what E would stand for? Be electromotive force, or EMF, instead of using V for voltage. I'm going to leave the choice up to you, and you will likely catch me flipping back and forth between the two. Up until I came to work for the college, I always used V equals IR. Voltage equals current times resistance, because that was what I was taught when I did it in a physics course. But in a lot of the trade books that you'll have, especially books you'll look at when it's time to study for block release, or perhaps your textbook, you will often see E equals IR used in the trades, and E just means electromotive force. We're talking about voltage in both cases, so it's the same thing. So E is typically voltage. And I'll put here, let's throw in, we'll throw in the or V, so you can use either one. I is current, R is resistance, and resistance is measured in ohms, which is this kind of funny little symbol. Now you'll notice there's no millis or kilos or anything in front of these. When we use this formula, all the units need to be in base units, which means there can be no milli, kilo, etc. All right, so you can't have those. You're going to have to convert to the base unit, calculate, and then if you're asked to put it in millivolts, you'll have to convert back at the end. So that's one of those kind of important things to note, that you need to be in your base units when you're calculating. Now, why do I have these two pictures here? Well, this is just the simplest possible circuit. So what Ohm's law does is it relates the voltage coming from the battery to the current flowing through the wires given the amount of resistance here. And we can often relate this to, say, a water supply. So let's say we have water going through a hose. Our water is supplied by a pump. Our pump provides the push for the current to occur. In electrical terms, this would be voltage, or our battery. It pushes current through the hose, and then the nozzle regulates the amount of flow, so it is like our resistor. Now, electrons don't just spill out the end because they need a closed circuit. They need to be connected back to the water supply, if you want to use that analogy, in order to have flow, so we don't have spray. But a pump is like our voltage, water flow is like the current, and then a nozzle that you can control is like a resistor. So what happens if we change those? Well, let's say we don't change the pump, but we make the opening larger, provide less resistance at the nozzle. Well, you will get more current because more water can exit. That tells us that if we decrease resistance, if we have less resistance, so I'm losing my pad here. If we decrease resistance, current will increase, which kind of makes sense to us. It should make sense. Those are inversely proportional. We discussed inversely proportional last semester. So they're inversely proportional. Notice they're multiplied together. And when we did inverse proportions, we always multiplied our two units together. Just get rid of some of that text just to make it a little easier for us to write. Okay, so that's if we change the resistor. Well, what if we leave the resistor the same? We're going to leave the nozzle at the same setting. but I want to increase current flow. Well, we could increase the amount of pressure at the pump. We could put a larger pump on. If we think about it like a tap, we could open the tap further, okay? So we could put a larger pump. If we have a larger pump or more voltage, we will also increase current. You'll notice in this case, these ones are directly proportional because they're on opposite sides of the equal sign. Okay, if they're on opposite sides of the equal sign, as E goes up, current is going to go up. So the more voltage, the more push, the more movement we're going to get. But if you just think about people going through a hallway, unfortunately with COVID, this doesn't happen so much, but you're at the grocery store, the more people that are in a lineup or at a craft fair, maybe you guys don't do craft fairs, this may be a bad analogy, but the more people there are, people don't stop because there's people behind them that keep them moving, they keep pushing through. Okay, so there's your voltage is all the people behind trying to get through, and that keeps the flow going, which is like your current. So the more push, the more current. All right. Now, what if the current doesn't change? Well, if current doesn't change, let's say the current doesn't change. If you increase voltage and current doesn't change, that can only mean one thing. That means you have more resistance in your circuit. Okay, so again, those would be directly proportional. You'll see E is directly proportional to either of the terms on the other side, assuming one of the others stays the same. So just kind of thinking about those things can kind of help you predict what would happen if something's adjusted in an equation. You're going to see that when we get to circuits, we'll be able to do some predictions based on thinking about, well, if voltage stays the same, where's going to be the most current, where's going to be the most resistance, and etc. All right, let's go to the next slide. So what are two other ways that we could write Ohm's law? So I started out with a review of algebra because I wanted to make sure you could rearrange these. So there are two other ways to write Ohm's law. We can write Ohm's law is I equals something. Well, if I want I alone, I would have to divide both sides by R. Dividing both sides by R, current is equal to voltage divided by resistance, or V over R. So there's one of the laws we could have. What's the other thing? We have it solved for E. That's the way that typically you memorize it, and you will need to know these. They will not be given to you on a block exam. The other one is, okay, what about R? How do I calculate R? R equals what? Well, to get R by itself, we divide both sides by I. R is equal to voltage divided by current, or V over I, depending which formula you want to use. So those are our three currents. Now, I know some of you are going to say, but what about the triangle? Because if Jeff has touched this, he's probably done a triangle. If you know how to do this, you don't need a triangle. You have the skills in order to separate them, but there is a triangle that makes easy calculation, and we often use it in the trades. What we say is E equals I times R, okay? So what you do, and it's really hard to do this with a, oh, that's not going to work either. I'm not sure if there's a way that I can do this no, I don't think I can. Looking to see if there's an option, but no. Let's go back. Whoops, too far. So what you do, and usually I like to use hands on the board to do this, but what you do is if you want to find, let's say you want to solve for E, okay? If we want to solve for E, we cover E up. And we get I times R is the formula. E equals I times R. If you wanted to find out resistance, we'll cover up resistance and you get E on top of I, which here resistance is E on top of I. So that's how you use that triangle, but it is very hard to explain how to use it when I don't have all of the typical things, the typical hand gestures I can use when I'm in the class. Now, for the purposes of math, because we are in math course, I am going to rearrange the formula rather than using the triangle. Triangle is your choice if you wish to use it, but because we are in a math course, we're going to put an emphasis on doing the math in the math form rather than just going off of a triangle. The triangle is a good way to memorize the formula though. So here's our first example. I just have a few questions. There's not too many. I've got 4 examples and then 1 or 2 examples with the power law. So really not too many examples. So this question says, sketch the circuit using common symbols. So you'll see here we have a battery and we have a resistor. So there's a couple different ways you could draw it, but a battery is typically these little dashed lines. The shortest side is always the negative. And then we draw our wire. Now we need a resistor somewhere. So you can use either one of the resistors. I like the zigzag. That's just the one that I've used the most. And you see it both ways. Okay, so there's our resistor. So this is 12 volts at my battery. And then over at my resistor, I have 470 ohms. And our wires are just drawn as lines. Oftentimes we'll draw them in squares. It doesn't necessarily have to be, but it's just, I find it easier to keep track of information when it's drawn that way. Of course, that's not how the wires look in real life. Question 2 says, calculate the current in the circuit in milliamps. So for calculating current, so we have a voltage and we have a resistance. What is the current? So Ohm's law says that E, voltage, equals I times R. We want I by itself, so we're going to divide by R. So current is equal to voltage divided by resistance, which is equal to 12 volts divided by 470 ohms. Ohms is this little kind of weird symbol, which is equal to, now this is going to give us just amps. Remember, it only gives us base units. So this gives us 0.026 amps. Now the question said, calculate in milliamps. To go from amps to milliamps, we want to multiply by 1,000. So that takes us back to that review lesson. So we have 26 milliamps of current. Okay? So not a complex calculation, very straightforward. Question 2, you'll notice we have a resistor here drawn a little bit differently. So we've got the other symbol for it. We have A here, this is an ammeter. So this is just where we're measuring our current. It doesn't really change anything in the question, not until you get to more complex circuits. So next week we'll deal with where we would put the ammeter and why. And then we get our battery over here. So calculate the value of the resistor in ohms. So we want to know, what is the resistance in ohms? Given the ammeter measures 4.556 milliamps and the voltage across the resistor, so the volts here, voltage is 12.3. Okay, so we're just looking at a piece of a circuit. We have 12.3 volts. The current is 4.556. That also will line up with the current here at the resistor. So how many ohms do we have? Well, the first thing we need to do is convert. Okay, so we need to convert to amps. So 4.556 milliamps. We have to divide that by 1,000 in order to get to amps. Equals 0.004556 amps. So a lot of decimals. That's one of the reasons why we like to use the term milliamps, is it eliminates some of those. Now 2 we can calculate. All right, so resistance, let's use Ohm's law, E equals IR. We want resistance alone, so we're going to divide both sides by I. So R is equal to E over I, which is equal to 12.3 divided by 0.004556. When there's double digits, I sometimes miscopy things. So I have to kind of say it out loud and think carefully. This gives us a resistance of 2,697 ohms. We could write that in kilo ohms if we wanted, but that wasn't required for the question. So again, straightforward math, the conversions are the most difficult part. You don't have that many conversions on the SAM quiz though. I just want you to practice, but it's important to remember those conversions because you'll see them come up again and again. One example of why conversions are important, my husband was doing a block exam. He works in wastewater treatment, and one of his block exams was asking him what the amperage of a pump was. Now they don't really have to do electrical work, but they need to know some of those pieces. And he made a mistake between milliamps and amps. And unfortunately, that mistake, he was one question short of a pass. Had he done that question correctly, and he knew the minute he walked out, he said, oh my goodness, I screwed that question up. But that one question would have meant the difference between, you know, getting a pay raise when he wrote that time or getting it a year later when he wrote the exam again. So it's important to make sure you do take the time to learn and memorize the conversions, even if you might not see the usefulness of it now. Having that knowledge in the back of your head is quite important. All right, let's go on to the next question. So I've got two more examples for you. So in this question, the ammeter measures 0.5 amps and the resistor is 15 ohms. What's the voltage supplied by the battery? So here we have 0.5 amps, we have a resistor of 15 ohms, and we want to know what's the voltage. So when there's only one thing in a circuit like this, so the ammeter is just a measurement device, it's not actually taking a load, the voltage here is the same as the voltage here, okay? So in order to figure this out, we want to use Ohm's law. So E equals IR. We don't have to rearrange it because we're looking for volts. Current is already in amps, so I don't have to change it. So 0.5 amps times 15 ohms. Nice, easy question. And we get 7.5 volts. So that's probably the easiest question of the lot because we had no conversions to do there. One more example before we do the power law. The power source in the circuit shown supplies 120 volts. You'll see this symbol here. This symbol means AC power. This would be like power coming from your wall. Cars use DC, direct current, whereas that's from a battery source. So a battery source is direct current. AC power is alternating current, which the electricity in your house is going to be alternating current. Anything that doesn't use batteries is going to rely on alternating current. I don't know if we'll get to talking about any alternating current or not. DC circuitry is what's most important for you. So the power source supplied shows 120 volts. So this is our 120 here. What resistance would result in the fuse or circuit breaker to trip if it's rated for 15 amps? So here's our circuit breaker or a fuse. And okay, what resistance here is going to result in too much current here and make it break? So what resistance would give us more than 15 amps? So we're just doing the same kind of question where what's R going to be? If voltage is 120 and current is 15. Well, we can figure that out. E equals IR. So we know rearranging it, we want to get R by itself. So we're going to divide both sides by I. So resistance is equal to voltage divided by current, which is equal to 120 divided by 15, which gives us a resistance of 8 ohms. So let's think, will the circuit trip if the resistance is more than 8 or less than 8? Remember, the current can't be over 15 amps. So if we put more resistance, if we block more current here, the current's going to go down. Does that make sense? So more resistance decreases current. It's like closing off the nozzle on the hose. If we decrease the resistance. So there's less restriction. That's going to allow more flow. It's like adding wider hallways or wider aisles so more people can pass. So that's going to increase. So decreasing resistance will increase current. So the resistor needs to be 8 ohms or larger. Okay? If it's smaller than 8 ohms, it's going to let too much current go and it's going to cause a fault, which will overheat the fuse and cause it to melt. It's actually a safety feature. We use fuses all the time to protect things. All right. Now let's quickly look at the power law. Just 2 quick examples. It won't take us too long. So the power law, and this is why I like to use E instead of V. Okay. The power law is PEI. I always say if you need some help to memorize it, PEI is power. Last year they gave me another one and they said, well, you could use PVI. Okay, if you want to. And they said the how you remember that one is POGI is very important. Perhaps more important this year than ever before with all the COVID pandemic. So you could use V instead of E if you want. And if you want to remember power, I like power equals PEI, and I'm not an Islander. So I'm just using that one because it works. Maybe I've been here for 10 years, but I still don't think I'm an Islander. Actually, it's more like 11 years, almost 12. But the POGI is very important. That's another one that kind of stuck with me. That was thanks to last year's students. So that's a really good one for us to remember. Maybe it was the year before. I think it was the year before they gave me that one. All right. So power is always measured in watts, just like you get wattage rating on a light bulb. Again, if we think about power, if you have a more powerful pump, that means you're going to have more push. So more power means more volts. That makes sense to us. And that's what this equation says. If we increase power, this side has to increase too. So we increase voltage, or more power will cause an increase in current. Okay, either one of those will occur. Now, when we look at voltage and current, though, they're going to be inversely proportional because they're multiplied together. All right, so you won't have to worry too much about those little things, but sometimes it can help us to think about problem-solving context. But next week, we'll kind of get into some of the problem-solving challenges. What 2 other ways could the power law be written? Well, we can write it for E. So E equals, dividing both sides by I, E equals power over current. Or we can say I, current, is equal to power divided by voltage. So those are the other 2 ways you can write the power law. Again, if you can rearrange it, you do not need to memorize 3 different forms. You memorize one and you use the math skills that you've learned this year or that you've refreshed this year. You can use a triangle if you want. Power, voltage, and current. And again, it's just like using it the other way. If you want to know power, cover power up and it's E times I. If you want to know I, cover I up and it's power divided by E. So you get the same kind of scenario. So very quickly, I've got 2 examples and then we'll finish off this lesson. How much power is used by a light bulb which draws 3 amps from a 12-volt battery? Well, power equals current times voltage times current. So power is going to be 3 amps times 12 volts, which gives us 36 watts. Another one, how much current is drawn by an LED bulb rated for 0.5, excuse me, 0.5 watts if it draws 12.3 volts of power? Yeah, I guess it's volts of power work. Sometimes it's hard to think of which terminology to best use. It's got 12.5 watts of power. It draws 12.3 volts of EMF. So, well, power is equal to voltage times current. So 0.5 is equal to 12.3 times our current. Divide both by 12.3. Current is equal to in this case, power divided by voltage, or 0.5 divided by 12.3, which gives us 0.0407 amps, or is equal to 40.7 milliamps. So that's just, if you multiply that by 1,000, you get your milliamps. Last example for the day is one final power question. What is the resistance of a light bulb that draws 4.3 watts of power from a 12-volt source? Well, power is equal to voltage times current. There is no resistance in that formula, so what do you do? Well, we did another formula today. Voltage is equal to current times resistance. So this is a two-step question. If I can calculate current, I know voltage. If I can find current, I can get resistance. So we're going to use our power formula to find the current, and we're going to plug that in and find the resistance. So it's a two-step question. So we have 4.3 watts is equal to 12 volts times our current. Divide both sides by, oops, I'm getting carried away here. There we go. Divide both sides by 12. Cancels out. And we get current is equal to 0.36 amps. Now we take that current and we plug it in over here. So we take 12 volts is equal to 0.36 amps times resistance. Divide by 0.36 on both sides. Just really simple algebra. And resistance is equal to 12 divided by 0.36 is 33 ohms. So this is supposed to be an R. My apologies. It's one of the messiest R's I've written. There, and that finishes off that section. So all of the calculations are pretty straightforward. Do watch for the occasional conversion. I will have you do those milliamp to amp, or use a few. You may see kilo ohms in a couple of places. So just do keep an eye out for those, because those are simply calculations that you do need to keep in mind as you go forward and as you prepare for your block exams and your units with Jeff.